And hello and welcome to the final video in this series where we do the last bit of paper 2 from the end of year test. So this is part 3 with the two, probably everyone will agree that these are the hardest questions in the paper. It is the other section B question that is hard in a funny way, we'll get back to that. And then it's the question 7 from section A, which is ridiculously difficult. So if you couldn't do that one, you really shouldn't feel bad. We'll get back to that. Please remember that these are the last 24 marks that you need if you want a grade 6 or 7. Definitely if you want a grade 7, you could probably get a grade 6 without solving these two, or by solving just the easy bits of question 9. But of course, if you're super ambitious, this is the stuff that you need to prepare yourself for. Because yes, the questions are hard, but also yes, that is exactly the level of difficulty that appears every single year in some of the exam questions. So let's dive into it. Question 7 is clearly about complex numbers. It is also two simultaneous equations with two unknown complex numbers. So they get to meet again. And it's only a 6-mark question, so you would expect it to be something that is done with quickly, but you would be wrong. The first 2 marks aren't that hard, they're just strange, because they start by asking us to prove something that we have already learned in class, that we already know, and I guess there was even a proof in the book. But we have to prove that if W is a complex number, then the product of W with this W star, which means the complex conjugate of W, is the same as taking the modulus of W squared. And now we have to give a proof of it. So how would you do that? Well, we kind of need to talk about what it means to do the complex conjugate. And for that, we can basically only say that if we talk about the Cartesian coordinates of the number. So the key to get started is to assume that W is equal to something like A plus I times B. Because if we assume that, then the complex conjugate is simply A minus I times B, and then we can calculate the product, W times W star, and that we get is A squared, and then we get IB times minus IB, that is minus IB squared, and then we get A times minus IB, and we get A times IB, and those two cancel out. So it's like a product of a sum with a difference. We only get these two terms, and the I squared becomes a minus, with this minus becomes a plus, so altogether we get A squared plus B squared. And just so happens that the length of W squared, so the length of W, that's this Pythagoras calculation, A squared plus B squared in a square root. But then we do that squared, and that removes the square root. So what do you know? We get exactly the same thing. And we could say these are the same, which was what we were told to prove. So that's a proof that these two things are equal to one another. And then comes question B. There are only 4 marks left. And we're being told that now the modulus of W has a value 2 times the square root of 5, and we have these two equations. So simultaneous equations with complex numbers is already pretty nasty. When we start to do multiplications in those equations, they are no longer linear because we have set multiplied with W, and we also have some set squared going on. So they are non-linear, and finally, using the complex conjugate of one of the numbers makes it even more confusing. So that's 3 different ways of making a situation that you haven't really seen before. And that's so nice of them, isn't it? You have to come up with an idea here. And the way to come up with the idea is to really have in mind what we were just proving in question A. There is a very clear reason they asked us to prove this thing, is to make sure that we have it in fresh memory, that if I ever get to multiply W with the complex conjugate of W, that is the same as the modulus of W squared. And the modulus of W is the value that we're being told. That's 2 times the square root of 5. And squaring that makes it even nicer, because then the square root of 5 stops being a square root. So those are the thoughts we have. It would be really nice to have W multiplied with W complex conjugate. So that's when I look at the question. Maybe you can see my pointer. And I look at the left-hand sides. It says one left-hand side, that's 5W conjugate, and the other one has set multiplied with W. So I think this is actually the only places where W appear. It would be mighty nice to multiply the two left-hand sides. Even though that's something that in a simultaneous equation situation we never really do. We prefer just adding and subtracting and multiplying with numbers, but multiplying the two left-hand sides is weird. But if we try and do it, so the left-hand side, if I calculate 5 times W conjugate multiplied with Z times W, that would be the same as multiplying the two right-hand sides. And that, it looks so scary that one is tempted to not even try and do it, because we get first this 1 minus 3i times Z squared times 10 plus 10i. But if you look carefully at this, in 1 minute I'll multiply W conjugate with W, and I'll just get a number. So I'll just have a number times Z on the left side. And the other side, it looks long, but these two brackets, they are like concrete, known complex numbers, so I can just multiply them together. And then I'll just have Z squared on this side. So it starts to look a whole lot like a quite simple equation about Z that I could solve. And that's exactly what they're asking. They're asking to find the value of Z. So that's what I'm going to do. The left-hand side becomes 5 times W times W conjugate, which is the norm of W squared. So that is 2 times the square root of 5 squared times Z equals, and here I could go Z squared times, and then I'll multiply these two brackets. What I get is first 1 times 10 is 10. Then I get 3i times 10i. That is minus 30 times I squared. So I squared is another minus, so I actually get plus 40 from these. So 30 added from these two terms. So 10 plus 30 is a real part of 40. Then for the imaginary parts, I get 1 times 10i, that's 10i, and then I get 3i times 10, that's another 30i, but they get subtracted. So it is 10i minus 30i, that's minus 20i. And simplifying the left-hand side, so this is 4 times 5 times another 5. That's really just 100 times Z equals Z squared times 40 minus 20i. We can divide both sides by 10. So it says 10Z equals Z squared times, then this gets a little bit nicer, 4 minus 2i. And then we want to solve this equation. Now, there is one very clear solution to this equation, and that is that Z could be 0. We'll get back to that in a minute. And if set is not 0, then we can divide with it, and then it really just says that set 10 is equal to a set multiplied with this. So it means that set is equal to 10 divided with 4 minus 2i. The first solution, this guy, does solve the equation that we get when we mix the two equations. But notice that sometimes when we do that, we only get one equation, and that equation might have some solutions that do not solve both the original equations. And we can see quite clearly that set being 0 is not going to solve really any of the two equations, because the left-hand side here is going to be 0 times w, so that's 0, and that's never going to be equal to 10 plus 10i. So this one can be ruled out, even though it showed up. And then we only have this one left, which is the value of set, except that we need it on a specific form, like a plus bi. So for that, we just need one more trick, which is to use the complex conjugate extension. So we take this fraction and we extend with 4 plus 2i in both numerator and denominator. And then we get a numerator that is 40 plus 20i, plus 20i, and the denominator becomes 4 squared plus 2 squared, that is 16 plus 4, that's 20. And then it gets really nice, because 40 divided by 20 is 2 plus, and 20 divided by 20 is really just 1 times I. So your A value is 2 and your B value is 1. Wasn't that a lovely question? And finally, there is this notorious question 9 that many of you told me you had quite a traumatic experience with. It is the last question, which means that once you get to it, you're really, really tired. It's also very long. It has 18 marks in it, so there's plenty to do. And all of that makes it difficult. And then there is one more thing making it difficult that we'll get back to later. But you should really appreciate that even though this is paper 2, almost all of this question, because this is about vectors in 3 dimensions, almost all of the calculations are stuff that we can do without the calculator. So let's try and dive into it. We get a line that's called L and a line called M, both of them given by vector equations. So when you look at that, you think, okay, there's a point that the line goes through with coordinates 1, 2, minus 3 for the first one, and here's a point for the second one. And then there is this direction vector pointing the direction that the line is moving in when it moves out of this starting point, so to speak. And we all know that. So in question 1, we have to show that the lines actually intersect at a point called A, and we have to find the position vector of A. And to do that, we simply set up, let's go here. We go to our answer booklet, because we're not allowed to write in the page with the question. And what we want is to have the vector that calculates any point on the first curve. That's like 1, 2, minus 3 plus S times 2, 3, 6. And we want that to be equal to whatever point the other vector equation makes. That is 9, 9, 11 plus t times 4, 1, 2. You always have to stop and say, do I actually want two different values, s and t, or do I want it to be the same value? In this case, it's really just a point that lies on both lines, and it's not like s and t are some model of time passing by, and we want to be in the point at the same time for both lines. So in this case, the right thing to do is to say it doesn't have to be the same value that S has in this as T has, which means that we have, in fact, 3 equations with 2 unknown variables. Very commonly, we can't solve all 3 equations and get a solution, which means that very often we get the answer that there is no value of S and a value of T where this makes the same point as the other one, which would mean that the 2 lines did not intersect. But we're being told to show that they actually do intersect in this case. So probably we're going to find that in this case there is a solution. But what we do is set up the equations. So one equation says that 1 plus 2 times S has to be equal to 9 plus 4t. The second equation says that 2 plus 3s has to be equal to 9 plus t. And that one is particularly nice because we can very easily get a value for t by just subtracting 9. So t is equal to 3s minus 7. And if we take that and put into the first equation, then it says that 1 plus 2s, we could say this is the first equation again, is equal to 9 plus 4 times 3s minus 7. And expanding that, we get, let's write it here, 9 plus 12s minus 28. And then adding 28, subtracting 9, that's the same as adding 19 to, wow. Let's just, let's move 2s to this side, then we get 10 times s. And on the other side, we have 29, and we subtract 9, we get 20. And that means that s must be 2. And of course, then we have the value of t standing up here. So t becomes 3 times 2 is 6 minus 7, that is minus 1. So we know that if the x and the y coordinates have to be the same, then we already know that s must be 2 and t must be minus 1. What we don't know yet is if that actually works, because we haven't even looked at the set coordinates. So for s equals 2 and t equals minus 1, we can calculate the set coordinates. So minus 3 plus 6s we get is 12 minus 3, that is 9. And if I do 11 plus 2t, that is 11 minus 2 is also 9, so they're the same. So yes, they intersect. Because the solution that makes the x and the y coordinate the same actually also makes the z coordinates the same. And if I want the intersection point, they call it A, I can get the position vector of A by just putting either the value of s into the left side or the value of t into the right side. I'll choose the s one, so we can do 1 to minus 3 plus 2 times 2, 3, 6. And that's going to give me 1 plus 4 is 5, 2 plus 6 is 8, and minus 3 plus 12 is what we calculated before, is the set coordinate 9. So that was the answer to question A. Question B asks us to verify that both of the lines, they lie in a plane that they call capital pi, given by the equation 2y minus z equals 7. So now we think, what does it mean to lie in a plane given by an equation? Well, the equation is a sort of tester that tests if a point belongs to the plane. And the point will belong to the plane if the calculation 2 times the y coordinate minus the z coordinate gives us 7. So why don't we just take any point on this line, calculate it like this, with an x-coordinate, a y-coordinate, and a z-coordinate, and check if the x, y, and z-coordinate fulfill this equation. It's easy to get a little bit confused because we're not going to use the x-coordinate at all, because the x-coordinate is not mentioned in the equation, but that's something that happens. And then afterwards we can do the same with this, and that's what we are about to do. So if we go back. So for question B, here we go. We first assume that x is the x-coordinate of line L, that is 1 plus 2s. We take the y-coordinate, that is 2 plus 3s, and we take the z-coordinate, that is 9. No, it's minus 3 plus 6s. And then we check if it obeys the equation by calculating 2y minus z, and that's going to be two of these, that's 4 plus 6s, and then we're subtracting minus 3 plus 6s, and we see that the 6s and the 6s, they cancel out because we are adding them and subtracting them, and we just get 4 plus 3, which is 7, which is exactly what we wanted it to be. So from there we see, so yes, L is in the plane, because for any value of s we will get a point that obeys the equation for the plane. So now we do it for the other one. We take x to be 9 plus 4t, we take y to be 9 plus t, and z to be 11 plus 2t. And again, we calculate what is 2y minus z. So now it is 2 times 9 plus t, and we subtract 11 plus 2t, and we see again we have 2t, and we subtract 2t. They cancel out, and we just get 2 times 9, that's 18, minus 11, which again is equal to 7. So yes, m is in pi, which is what they asked us to show. Then it moves on, and we are being told that there is a point B that has a position vector minus 3, 12, 2, and there is a line that goes through B and is perpendicular to the plane that we were just working with. And that line intersects the plane at a point C that we have to find. So we just have to kind of shake the head and understand the information. The key thing is that if a line goes through B, then we already have a starting point for the line. And if the line goes perpendicular to pi, then we get a direction vector for the line by saying we just need a normal vector to the plane. And it's so nice that when you have an equation for your plane, then the coefficients of x, y, and z, they are coordinates for a normal vector. So there is a free normal vector with the coordinates 0, because we have 0 times x, and 2, and minus 1. And that normal vector can be used as a direction vector for this line that goes through B. And then we have a full description of this third line that looks exactly like these two. And we can ask, when does that third line intersect with the plane? That is the strategy. So let's get started on that. Here we are, making a bit more space on the paper. For question C, the first thing we do is that we have a normal vector with the coordinates 0, 2, and minus 1, the coefficients of x, y, and z in the equation for the plane, used as direction vector, makes a vector equation of the form x, y, and z equals Now the starting point, that would be minus 3, 12, and 2, plus a parameter. So we have already used both s and t, so maybe we want to call this one r, times 0, 2, minus 1. And we want to intersect that line with the plane, so we want to ask, when does the x, y, and z coordinate obey this equation? 2 times the y coordinate minus the z coordinate has to be equal to 7. So we put in the y coordinate, that is now 12 plus 2r, and we subtract the z coordinate, that is 2 minus r, and say that must be 7. In this case, we see that the r's don't just cancel out, so obviously this line is not going to lie in the plane because it's perpendicular to the plane. But what we do get is an equation where we can solve for r. So we get 24 minus 2, that is 22. And then we get 4r plus another r, that's 5r, is equal to 7. So we can subtract 22. We have 5r is equal to 7 minus 22. That is minus 15. So r is equal to minus 3. And that's really nice. Again, when we get an integer, then something tells us that things are going right. That's the value of r that we have to put into the vector equation in order to calculate the point that is both on the line and in the plane. So that's what we do. The point we are calculating is called c, and we are calculating a position vector for c. And that's by taking minus 3, 12, 2 plus the r value times the position vector 0, 2, minus 1. And then we get the coordinates minus 3 plus 0. And then we get 12 minus 6, that is 6. And we get 2 plus 3, that is 5. And that is the coordinates of c. And that was c part 1. Part 2 says, hence find the length of vector BC. And if we say this is CI, and we do that, CII, by first calculating the vector. So BC, the way you calculate the vector is by taking position vector of C and subtracting the position vector of B. So that is minus 3, 6, 5, and B was just given, so we are subtracting minus 3, 12, and 2, and then we get 0, 6 minus 12 is minus 6, and 5 minus 2 is 3, and the length of BC, which is what they asked, is the square root of the squares of the coordinates, so 36 plus 9, so that is the square root of 45. And this is the only place in this question where we actually need a calculator. So if we want an approximate decimal value, we just put it into the calculator, 45 to a half. So that's approximately 6.71. And finally, for question D, they say find the reflection of the point B over the plane pi. And this is only a 3-mark question, so it's supposed to be easy. And the good news is that it is actually super easy, and you'll see that, but I can totally understand why you would be very confused at this point. I am too. And I can tell you exactly what is the confusing thing. So if we try and draw up this is not really part of the question, but we'll get the right idea and we'll see why it is that we are being confused. And this is a good thing to actually be aware of, because that is the type of confusion that often comes on section B in an exam paper, because the question is so long and it's going in weird places, and then it's very easy to get confused. Because if you look, let's try and draw this. If we try and look at what happened in this question, then what we have is a plane. And if we think of this plane, sort of, we see it very much from the side. This is the plane pi. Then we had two lines, L and M, that happened to lie in the plane. So that's these two guys. And we found out that they would intersect in a point that they gave a name, A. And then came a point B that was not in the plane, and we were told to find the line that goes from B orthogonal to the plane, so that's sort of this line, and it meets the plane somewhere orthogonally, and that point, we call it C, and what we have just calculated is this vector BC, and I think by now you should kind of sense where this is headed, but let's first try and pinpoint what is the confusion. The confusion is that the line L and the line M and the point A have nothing to do with the problem anymore. They are completely gone. And we're now talking only about the plane and the point B and the point C that we just found. And much of the confusion is often that you're trying to have everything going in your head at the same time. And you're like, what about the lines? Do I need those? Well, no. The lines and the intersection between them is completely irrelevant now. We have just moved somewhere else. If you manage to get that clear, and the drawing should kind of make that clear, what they're asking in this last question is to reflect B in the plane, which means that we want to go to the opposite side of the plane, or we want to find this point. And if you think that we have just found the vector BC, this vector, it becomes pretty easy. Because how about taking the vector BC and making it twice as long, and then adding that vector to vector B? And that is exactly what we're going to do in part D. We're going to take the position vector OB and add, not the vector OC, because that would give us the point C once again, but we're going to add 2 times the vector BC. And that's really it. So OB, where did we have the coordinates of B? They are -3, 12, and 2. And now we're going to add twice the vector 0, -6, and 3. And then we get -3 doesn't change. We get 12 minus 12, that is 0. And we get 2 plus 6, that is an 8. And that, ladies and gentlemen, is really just the reflection of B. So we could call that B prime. And if they want a point, the difference between a position vector and a point is that the point looks like this, -3, 0, 8. And that is the end of this question. So you'll notice we needed the calculator one single time for a square root. Everything else is hand calculations. And if you manage to get your confusing thoughts put away about, like, what about those two lines and their intersection, then everything is actually surprisingly straightforward. And that is so annoying, because I totally understand why this question is hard. Anyway, that's the end of it all. I hope you enjoyed some of the videos and that you endured the rest. And I hope you can use it to improve your skills and get some training for whatever challenges lie in the future. Have a nice summer break, everyone.